Hello, welcome to the FRQ of the day. I hope you're doing good. So today we're going to do the 2007 number 4. So let's see if you can figure this one out. So this one says investigators at the U.S. Department of Agriculture wished to compare methods of determining the level of E. coli bacteria contamination in beef. Two different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of a certain type of beef. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown below. And so there is the method A, the level of contamination for, first of all, there's one specimen. They used method A on it and they used method B on it, and they got these two different levels of contamination. Then here's the second specimen. They did method A and method B to measure the level of contamination and so forth. And they did it for 10 different specimens and got this data. Is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide a statistical justification to support your answer. Okay, so if you want to pause the video and give this a shot, that'd be great. All right, now this, when it says, provide a statistical justification, is there a significant difference? That is basically asking for you to do a test, okay? It's asking you to find a p-value. There's a probability that we would get sample values this unusual, assuming that the null is true. In other words, in this case, assuming there's no difference. And guess what sort of test we should do? Well, who's mean? That would be Mr. T. Mr. T is mean. And these deal with means. It says the mean, and you immediately think of T. So we're going to do a T test, okay? Now, you see these two lists of numbers, and it may be tempting to say, we got two samples, we're going to do a two-sample T test. The reason you cannot do a two-sample T test, or you're not supposed to, is the fact that we don't have independence here. We don't have independent random samples because the data has been paired. This one goes with this one. I mean, each of these specimens, if there's a specimen that has a high level of contamination, that means method A, and like this one, it looks like it has a high level of contamination. So these numbers aren't independent here. This one goes with this one. If it has a high level of contamination, it's going to be high for both method A and for method B. But if it has a low level of contamination, it's going to have a low value for A and B. So that's not independence. The occurrence of one is associated with a change in the value of the other one. So we have to do what is known as a paired t-test. Whenever it's this paired situation, you have to subtract these numbers. Say that minus that's like negative 0.3, and that minus that's 0.5, and that minus that would be 0.3, and so forth. And we do a t-test with those differences. That's what we're going to do. And of course, whenever we do a test, we have to do the FAME acronym. So here is our test. So this is what is known as a paired t-test for a mean difference. Okay, is what it is. All right. And so then our null hypothesis, and so that's the T of your FAME. You have to state the type of inference. Then you have to state your hypotheses and define your variable or variables. And then your null hypothesis, there's no difference. The mean of the differences is equal to 0. The alternative is that not equal to. It didn't imply here that one works better than the other. It just said, is there a difference between the two? Okay, so we go with not equal to, where mu sub d is the mean of those differences. In other words, the true mean difference of the contamination levels of E. coli for methods A and B, and we went A minus B. And make sure you state whether you're going A minus B or B minus A. So there's your hypotheses. Then after that, we have our assumptions or our conditions. And so here we go. So we've got, first of all, is it random or a simple random sample? It says they were randomly selected right there. It says they were randomly selected. All right. So the random conditions met. There must be at least 100 specimens like these for our population size, at least 10 times our sample size. That guarantees you that our formula for our standard error will work because we're using sampling without replacement here. All right, and then lastly, we do normality. All right, now normality, all right, of course, the central limit theorem says if our sample size is bigger than 30, we'd have a normality. It's not. So we're doing, it's just 10 here in essence. All right, so, or if it's said up in the problem, that it varied approximately normal anywhere. It doesn't say that up here. So we got nothing in that regard. So if that's the case, the third option is this. We're going to graph the data as long as we don't have outliers or strong skewness. In this case, yes, we'd graph the differences. Now, the way I get those differences quickly, by the way, it doesn't take long to subtract them like I was doing up there and just get the differences. But a quick way to do it, if you use your calculator, is I entered the data in list 1 and list 2. And so if you go stat and edit and then I did, those are that's the data entered in, so that's these lists here, and so I put A in list 1 and B in list 2. And then to find the differences quickly, I'm going to arrow up and highlight list 3, and then I'm going to say list 1 minus list 2. So I'm going to go second one, which is list 1. Notice list 1 appears in the command line. Then hit the minus button right there, and then go second 2 for list 2, enter, and there's the differences. And I'm going to do a t-test with those differences. So we have to graph those and make sure there's no outliers or strong skewness. And in this case, that certainly works out. There's no outliers or strong skewness, therefore normality is reasonable. So that's the proper way of wording that. Then we need our mechanics. We kind of come up with our test statistic and our p-value and our degrees of freedom. Degrees of freedom identify which t-distribution we're working with. It's for a one sample test, which this is effectively. All right, it's 10 minus 1 or 9. All right, and we can get these off of your calculator. Of course, like as we've talked about, I really doubt you're going to be using your calculator like this on this test. What's going to happen is, in my opinion, and in the opinion of any guru that I've heard talk about this test, they're just going to give you the p-value. And your test statistic, and they're going to ask you to do all this other stuff, to write the hypotheses and to check your conditions and to state your ending like we're fixing to do down here. But just to do that, what you could do is you go stat, you go test, and you go t-test. So you go t-test, and we are working with data which I have in list 3. The null hypothesis value is 0, and so list 3 frequency is 1. The alternative is not equal to, and so we go calculate, and that tells us our t-test statistic and our p-value there. And so there you go. And that formula, by the way, you say, how did I get that formula? Well, as we've talked about previously, our formula for our standardized test statistic, whether it be Z or T, is statistic minus parameter over the standard error of the statistic. Our statistic is the mean of our differences, which is just the average, that's 0.29, the mean of our differences. All right, and then our parameter is just 0. That's our null hypothesis value. It's just 0 there. And so then the standard error of the statistic is right here on page 2 for means. It is S over the square root of n, where S is the sample standard deviation, which you can get that off of your calculator. You could use one variable stats, but there it is right there when you do your t-test. And so that's your formula. That's really sort of unlikely to be in the exam. But what is very likely to be in the exam is this ending. So we've done our type of inference, we've done our hypotheses, we've done our assumptions or conditions, we've done our mechanics. All right, now the ending. We have to draw our conclusion with the p-value, and it's just like every other time we draw a conclusion with the p-value. With a low, if the p-value is low, we reject the null. Okay, and in this case, it's not low; it's above 0.05. It's above our alpha. All right, so I do not reject the null. There is not convincing evidence that, and then you restate the alternative. The true mean difference of E. coli level for methods 1 and 2 is not equal to 0. Thus, we do not have evidence that the two methods differ. So there you go. That's how you do that problem from the 2007 exam. And I would be honest with you, I'd be surprised if there wasn't something similar to this on your exam in regards to doing an inference thing like this. I think the other thing that you could do is you could make an interval with the differences, and 0 would certainly be in the interval, and so you wouldn't reject it. That's the other way you could have actually potentially done this problem. Of course, you still have to check your conditions and all of that, but we've talked about that several times this year. But that's it. If you have any questions about that, please send them to me, and I hope you just have a wonderful day.